The lesson is so huge that I'm going to do it over 2 days. So today will just be an introductory kind of idea, and then we'll go hard and AP style on Monday. But I do want to have at least time for questions at least one segment that evening. I don't want to be backed up 3 or 4. So here we go. The idea is estimating an area under the curve. That might seem like why would you want the area under an equation? It's super duper huge important in terms of calculus. I guess I'll just say it like this, and then we'll get to the applications Monday. But say you're going 30 miles per hour for 2 hours. You go 60 miles. Are you marking me with my hand gesture? Oh, okay. 60 miles, right? Now, in actual life, you don't go. That's a constant rate times time problem. Algebra is old as the hills. In actual life, though, you don't go a constant rate. You vary your speed, yeah? So to actually find out how fast you're going in real life, when your speed is varying, you can't just do one big 30 miles per hour, 2 hours calculation. You have to say, well, for this little time frame, I'm going this fast, so I can find out roughly how fast you go here, or how far you go here. And then recalculate another time region when your speed is a little different. And if you do that infinitely many times, you start to get a perfect picture of how far. Now, all that seems analytical or wordy. It doesn't really have a visual component to it. That's the area under the curve. All that connects to area under the curve, and I'll make how that connects clear on Monday. But just know that this is a big idea of calculus, a real big idea of calculus. And the what of it we'll get on Monday. So if we get area under the curve, there's lots of different kind of iterations of this, or little types of problems, variations in the problem. I'm covering left and right-handed midpoint rectangles, equal subdivisions, equation, and table. Okay? So that seems like a lot, but it's actually pretty straightforward. Here's what I'd like you to do. Consider the square root graph. Would you sketch that region? And when you sketch these, would you note to yourself, sketch it wide. You don't want it to scale necessarily. You want it to be really wide because it's going to help you. You're going to mark up the x a lot here. So the square root function would look like this. And let's say it goes to 8. There's 4. Half is 6. Half of that is 2. And obviously we could go 1, 2, 3, and all that stuff too. All right. You following so far? All right. Now, the idea we're going to talk about is what's the area of this region under the curve? And it's a kind of curvy region, so there's all these geometric figures we could do to estimate. We could do a triangle, for example, and that would be a decent estimate, right? We could do trapezoids, which we'll do later, and that's a really quality estimate, you know. We wouldn't really do anything like circles or anything like that. But your main estimation methods, we don't use triangles for reasons you'll see later. But the main estimation methods are rectangles and trapezoids, okay? We're going to do rectangles today. Now, surely one rectangle, if I estimated this with one rectangle, for example, I could draw here. I could find the area of that rectangle, and it would be a decent estimate, be an over an estimate of the true area, right? Right? Okay. One of the principles is if you do more rectangles, you'll get a better estimate. So if instead of doing one rectangle here, I could do maybe one rectangle at 4, and then one rectangle here, and that would be a little better estimate because this area here where I'm getting error would be less, right? Okay. We're going to do instead, if you look at the directions, we're going to use 4 right-hand rectangles. Now, what right-hand means, I will come to, but know first of all that I'm going to divide the region into 4 equal parts. If the total width if the total width is 8, and I divide it into 4 parts, then each little subdivision would be 2, yeah? So I'm going to have a rectangle at 2, from 2 to 4, 4 to 6, and 6 to 8. Each of those is going to be my base. Those are going to be the bases of the rectangles. Now here's where we go to right-hand rectangles. When you say right-hand rectangles, it tells you where to draw the height. In this first subinterval from 0 to 2, they call the whole interval 0 to 8, so the subdivisions are subintervals. In this first subinterval, I'm going to the right edge of the subinterval, which would be at 2, go up until you reach the curve, and that's going to be the height of my rectangle. So if this is the base, this is the height, then if I complete the rectangle, then that is my first rectangle. You follow? So in the next subdivision from 2 to 4, I go to the right edge because I'm using right rectangles. I go up to the curve, and then once I'm to the curve, that's as high as I'm going to go, and I go over, straight over, at a right angle because it's a rectangle. Make my second height. The next subdivision is at 6, so go to 6, go up to the curve, draw straight over until you get to the end of the subinterval at 4. And then at 8, draw straight over. I got 4 right-hand rectangles. You with me? Any questions? All right, cool. Now that's the visual part of it. The visual is very important. As you get really good at these, you'll start to rely on the visual less. But starting out, I strongly recommend you graph these. It's helpful. Okay, now this is the work I would like to see. We're going to find the area under the curve, or estimate the area under the curve using these rectangles. The area is estimated by, now that A stands for the true area under the curve, estimated by 4 rectangles. Base 1, height 1, base 2, height 2, base 3, height 3, and base 4, height 4. In cases where there are tons of rectangles, if I ask you for 10 rectangles, feel free to just give me the old dot, dot, dot in the middle from base 1, base 2, and then dot, dot, dot. Okay, so now we substitute. This is like pre-algebra. Formula, substitute. What's the base of each rectangle? 2, 2, 2, 2. Now here's where it's not so pre-algebra. This is where I start to get picky. I am fine if you use numerical bases. Put in 2, fine. Okay. I am not fine if you start to give me numerical heights. This goes to preparing you for the AP test and how it's graded. Okay. When you express the heights, you need to communicate in your notation where they came from. So this first height is here, yeah? Now, you and I know it's the square root of 2. Okay. But in terms of what I want to see, I want you to show me that is f at 2. The first height is what the function is, the y value at 2. The next height is the y value at what x? 4. And the third height is f at 6, and the last height is f at 8. All right. That's the substitution I must see. Now, there are 2 types of rectangle problems, where the subdivisions of the bases are all the same and where the bases are not equal. In this case, all the bases are the same, so you can factor out a 2. We can also start evaluating f at 2 is the square root of 2. In this case, the function I'm dealing with is the square root function. So f at 2 means the square root of 2. F at 4 means the square root of 4. F at 6 means the square root of 6, and f at 8 is the square root of 8. At this point, then, you can pick up your calculator and give me an estimate. And I think I am going to model this because I can save you some time in terms of getting this and the next step in if you are well taught. Do-do-do. Do-do-do-do. Sorry about the delay. Okay. I'm sure it'll give me a pop-up something. No, thank you. Okay, so here we go. Sorry. Man, my eyes are killing me. Okay, square root 2 plus, I guess I could just say 2, never mind. Just 2 plus square root 6 plus square root 8. Did you get 17.384? Okay. 17.384 then is good. Always give me 3 decimals. That's pretty darn good. If you consider what the one rectangle case, it would have been 8 root 8 for the base and root 8 for the height, and it would have been substantially more than that, I'm sure, because that would be this area, and we'd be getting a ton of error. This 4 rectangle estimate would be much better than that one rectangle case if I chose to investigate that, which I dropped out of my lesson for the interest of time. Are you with me? Okay, let's then consider the same problem, but in part B, left-hand rectangles. If you show the curve, half, and we're using 4, so go into 4 chunks, 0, 2, 4, 6, and 8. Now, again, each base, we're using 4 rectangles, so each base will be 2. If I divide 8 into 4 equal parts, I get 2 equals bases, or 4 equal bases of 2 each, yeah? So if I use left-hand rectangles, then in each region, I'm going to use the left side for the height. This always kooks students out. In this subinterval, the left side then means right here, which is a rectangle with a height of 0, and that's okay. In the subinterval from 2 to 4, I draw my height at the left side too. When I say draw the height, you go to that point, go up to the curve, and that's your height. Now, here we're starting to get a rectangle, so I'll slow down. This is the side of this rectangle from 2 to 4. So when I draw this over, I should actually draw that way until I get to 4. That's my. In my next subinterval from 4 to 6, I draw up. I go to x equals 4, draw up to the curve, and then I draw over till the right side of my subinterval, which is at 6, and I get a rectangle. And then my last height is to start at 6, go up, and over till 8, and I get 4 rectangles. You follow? Okay, now the analytical. Start with the formula. Area is approximated by 4 rectangles. Here we go. What's the base of each rectangle? 2. 2. 2. 2. You could, I suppose, start factoring that out now, but I definitely need to see the height. The first height is f at 0. The next height is f at 2. Then f at 4. Then f at 6. Plugging this or cleaning this up a little, I could take 2 out because of the greatest common factor of 2, and I'm left with 0 plus root 2 plus 2 plus root 6. If I did a little simplifying, I suppose I could have just kept it clean. Whichever you prefer, you can start simplifying or you can keep the pattern clean. At that point, it's pick up your calculator time. If you want, you can just go back and doctor this up a little. How could I just recall this and use it? Just take out the root 8. And I get 11.727. How about you? Okay? 11.11, not 17. 11.727. You follow? Okay, is this an overestimate or an underestimate? Underestimate. So I know that the true area is probably above 17.27 and below 17.384, yeah? The true area is in that window. Now I could tighten that window by, instead of using 4 rectangles, I could use 8 rectangles, or 10 rectangles, or 50 rectangles. Or I could even take the number of rectangles to infinity by using a limit, which we will do. All right, but later. For now, that's infinite rectangles. That's for another day. Let's talk midpoint. If you draw the curve one more time, 0 to 8, divide it into 4 subintervals. Now we're going to use midpoint rectangles. As the name kind of indicates, we're going to use the midpoint. The only question is midpoint x or midpoint y. It's the midpoint x. The midpoint between 0 and 2 is 1. So if I go to the midpoint, go up to the curve, and draw over, where do I draw the top of my rectangle? From where to where? The subinterval, the base of the rectangle is from 0 to 2. So the height of the rectangle, or that top side of the rectangle, should go from 0 to 2. Hi.
Hi.
How are you?
Good, how are you?
Good. 0 to 2. He is in this. No. He's in this kind of spot. So.
Oh. Okay.
Thank you. 0 to 2. So you can see then that this is a little funky because it's got a little bit of overestimate area and then a little bit of underestimate, which makes it probably better. Yeah, it's even better. So where's the next height going to be drawn? What x? 3. Yeah, the midpoint from 2 to 4 is 3. So you go to that point, draw up to the curve, and you draw over to complete the rectangle from 2 to 4. The next is at 5. Find 5, go up to the curve, and draw across, so your rectangle goes from 4 to 6. And then find 7, go up to the curve, draw across until you have a rectangle going from 6 to 8. Okay? So what's the first part of my analytical setup? Area equals, and then the formula. Base 1, height 1 through base 4, height 4. Telling the person, hey, I'm using 4 estimating rectangles. Okay? That's what tells the person I'm not using trapezoids, I'm using rectangles. Tells the person how many rectangles. It's an important step for the reader to understand what you're doing. Okay? What is the base of each? 2 of each. 2, 2, 2, and 2. Okay? The first height. We fight the temptation to start putting in numbers and we express functions. We say the height is the function at 1. The next height 2 is f at 3. The next height is f at 5. And the last is height at 7. Okay? We throw that into our calculator. Actually, we could start at 2. You could start, you could actually skip this step and just start, whatever. Square root of 1 plus square root of 3 plus, later on down the line, I think that would be what they would look for AP style. After that, then they would skip to the answer. So either which way, whether you express that or you go straight to your calculator, your answer is be a miracle if I don't forget to get out of the root each time. 15.227. Does that make sense that it's between the two estimates that we already had? Yeah, it is. 15.227, does that make sense? Okay. You follow with me? Pretty straightforward? Okay. Let's go to the back side then and do this from a little different angle. Same approach, but this time instead of a function, square root of x. They're going to give you a table. You don't even know what the function is. I gotta say, starting out, especially for me, I'm very visual kind of person, but I think even for visual people or non-visual people, a really rough sketch helps. Now, I don't, like I said, I really mean rough. It looks like the x's are 3, 6, 9, 12, 15, 18. In terms of a scale here, 8. I'm just going to go by ones. Like I said, it doesn't have to be pretty. 0, 5, 3, 7, 6, 4, 9, 3, 12, 8, 15, 0, 8, 3. Okay? If you want to try and smooth it out and draw a curve through it, fine, but I don't really need it. Okay, here we go. It says estimate the area on 0 to 18 using 6 right-hand rectangles. Now, let's first figure out the base of each. If the total region is 18 wide, and I'm dividing it into 6 rectangles, then each base is 3. I would typically call this my delta x. Okay? Each is 3. So my base is 3 each time. I'm going to have boom, 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 and boom. Okay. Now the heights. If I'm using right hand, then my first height will be at 0. The first region is 0 to 3. I would draw the height at 3. My next height, my region is from 3 to 6. I would draw the height at 6. Then 9. Then 12. Then 15. And then 18. Okay? So if I were to estimate the area here, base 1, height 1 through base height 6 height. What's the base of every rectangle? 3. F that, 3, F that, F that, 1, 2, 3, 4, 5, 6. Okay? My first height. My first region was from 0 to 3. I used the right-hand side. So the height I used was the function at 3. So my first height should be f at 3. Then I'm communicating to the person. This is where I got my first height from. My next is f at 6. My third rectangle is f at 9, then f at 12, then 18. Okay? You agree? Right? So if I take out a 3, because they all have the same base, and then I start using the tables, I'm going to start at f at 3, which is 7, and then I'm going to just start reading the next table value is 4, 3, 8, 0, and 3. So my estimate is 3 times 11, 14, 22, 25. 75.
Are there units?
What's that?
Are there units?
Good question. There will be, but not yet. That's an excellent question. Yeah, I guess. Okay, so 75 is my estimate. Pretty cool. I don't really know if this is an over or underestimate because I don't know. It's really about whether the function's increasing or decreasing, and it's kind of all over the place. So I wouldn't say overestimate or underestimate. I'd just say whatever. All right. Would you try the next one? Please look at the 2 critical points. It says 2 left-hand rectangles. I'll be right there. You try it on your own. Yes.
What does the top of that say base is?
Base is total region divided by 6 rectangles. I'm sorry, my handwriting is atrocious. Total region 6. I don't know if are you redrawing or are you just kind of going off your old picture? You don't have to. If you just prefer to just go off the new one, that's fine, or the old one, that's fine with me. Because it's only 2, really it's not a lot of drawing, it's just 0 to 9 and 9 to 18, yeah? I only need the heights then at 3 points, 0, 9, and 18, so that's 5, 9, and so what's the base of each here? Is it 6 or 3 or what? In this case, it's total region 18 divided by 2 rectangles, so each base is 9. The area then will be approximated by 1 base height plus 2 base heights, and that's it. The base of each is, we just said, 9. The only thing left to decide is where do I put my heights. If I'm using left hand, then from 0 to 9, I use the height at 0. The first height should be at with 0. The next subital from 9 to 18, I use the left side, so that's the function at 9. Therefore, that is 9 times 5 plus 9 times 3, 45 plus 18 is 63. Did you get 63? Do we agree? Okay. Try the last one on your own and we will be done. Try 0 to 18 using 3 midpoint hand rectangles. That means nothing. I forgot to scratch the hand. Sorry. Midpoint rectangles, not midpoint hand rectangles. Nobody has a midpoint hand. Left hand or right hand.
72. It's 72, not 63.
72. What did I say? 45 plus 27, because 9 times 3 is 27, not 18. I actually did quite well in arithmetic in school. You wouldn't believe me, but okay. 72, yes, thank you. No wonder I didn't get agreement. Good job. Where's your first height drawn? Have that what? 0, 3, I heard. Which one is it? 3, yeah, it's because it's midpoint. The interval from 0 to 6, the midpoint of that is 3. You're going to use 3. And then the next height will be halfway between 6 and 12. The midpoint is 9. The last one is the midpoint between 12 and 18, which is 15. So those are what you should be looking at in the table, those F values. Factor 3, what is F of 3, 9, and 15, please? 7, 3, and 0. Okay, so you get? The base should be 6, yes. Why did I have 3? Ay, thank you. Man, having a rough day. Lo siento, mijos. Okay, 6, 6, and there's another 6. So that's 6 times 10, so 60. Okay. Do we all agree with 60 on that last decimal?
Yep.
All right. You get the basic idea? Pretty straightforward? Okay. All right. Questions on what's the oldest that we have? 37? We still have 36? What the heck? What the heck? 36, let's finish. And maybe also knock out 57? Huh? Yeah. 36. Hit me.
So we're in the middle of
1?
one.
Oh, we were in the middle of 1. Yes. 17. One more, boom. Okay, let's stop it at 2 then. That's good. 36, 1, and 17. All right, so you've got this. I wish I would have done a visual here. You've got this circle that had an X-type sector removed. X is the angle of the sector. If you squeeze these two together, if I put my fingers here and here, and I brought those two together, then this would pop up and make a cone. So that X would no longer be visible, but where those two came to meet might be somewhere like here. Somewhere those two would come to meet, yeah? Okay then. The idea is they want the circumference of the cone and the radius of the cone. Surely because they come from that circle, they're going to have to do with the circle. That's the whole question. What's the relationship? Look back at the circumference of the cone. This came from the curve of the circle. Yeah, that blue is directly related to that blue. Once I squeeze those two things together, then that would be the distance from the base, right? So the circumference of the cone is the arc length. And I think that's where we started to leave off. Arc length is a fraction of the circumference of the circle, which means fraction of pi d, yeah? Do you agree? Alrighty. It's a part. This arc length is just a fraction of the total circumference. Let's go pi d. I think they told us in the problem that the radius was 10, yeah? So that means, boom. The part of the circle, the fraction of the circle that is there, we want the part that is there out of the total.
The diameter's 20.
Jeez, I am fine. Yes, thank you. Good thing you guys are on your game. Phew. We're making a key for BC. That's going to go badly. What about the fraction that is there? What's the angle of the arc that is there? X? We know 2 degrees in calculus, my friends. 2 pi minus x. Okay, 2 pi minus x over the total circle in radians, which is 2 pi. Okay, so if I do a little bit of cleanup, those 2 pi's don't cancel because there's a subtraction up top. but the pi's definitely can, and I can take 2 into 20, and I would get something like 10 times 2 pi minus x. That's the circumference of the cone. With that then, the radius of the cone is not too much further. What's the relationship between circumference and the radius? Circumference is 2 pi r. If the circumference I just found is 10 times 2 pi minus x, then r of the cone is all that divided out, yeah? 10, 2 pi minus x divided by 2 pi. And there you go. Cool? All right, 17. 17. Graph sine and 1 over sine on the same coordinate plane. Did I change this at all, or is it the same? It's what? It's the same, okay. All right, this is good review for the test. I will expect you to graph sinusoids well. I would choose a scale that would allow you to do that. Maybe I'm going to go maybe every 2 boxes to a pi over 2 or something like that. Okay? If I graph sine, I know that it does?
Yeah, mine's super.
Oh, shoot. Why did I say graph the calculator? That's not hard. Why can't you graph it by hand?
It's like 0.73.
It's 36, right? And 36. I'm trying to see if 36. I'm going to ask you these. Is it? Am I looking at the wrong set? Oh, I'm looking at set 38. What are you even looking at 38? Hi. What are you wondering what I'm doing with sine? Were you going to say something? No, I don't know. You're the teacher. I don't know what I'm doing. Isn't it obvious I'm clueless at this point today? I mean, come on. I'm even a race. All right, here we go. 17 on the set. You asked about 37. Here we go.
36.
36. Wow, I was actually at 37, so I'm glad you said that. Just about to hit 37. All righty, here we go. Now I'm talking. So it is a calculator problem. How about that? Cosine y equals x. All right. Is this starting to look familiar? All right. It says, find the x-coordinate of the intersection. So basically, is it how to do this in your calculator, or what's the point of the problem? Which are both. Okay. So you do need to be able to find intersections in your calculator. So go to your calculator and do cosine of x. Make sure it's in radians, first of all. That might have been an issue if you didn't get their answer. It might have been because you were in degrees. We don't do calculus in radians or degrees. We do it in radians. Okay, so you should get something like that, one intersection point. When you go to intersect in the Inspire anyway, you go to Menu, Analyze Graph, Intersection, and you give it a region where to look, left and right. And the minute you do that, you should start to see it. 0.739 is the x. Okay. Intersection x 0.739. Now, they said then compare that to the 0 of y equals cosine of x minus x. I think the idea, they're getting at there are 2 ways to solve any algebraic equation. You could graph each piece separately and see where they're meeting, which is to say cosine of x equal to x. And graph them separately. Or you could go one better and put them together and say, where does cosine of x minus x, the difference come out to be nothing. So besides solving that equation separately, you could also solve it together. If you were to graph, scratch what you have there, Control G. And call it cosine of x minus x. You will see a totally different graph. That's kind of cool. It's the combination of a linear function. It's like, I don't know if you realize what's going on there, but you have a slanted center line instead of a constant 2 plus cosine of x, where you're centered at 2 and cosine causes variation around 2. Now you're starting at negative x, and varying cosine causes variation along that line. So it's a varying center line. That's pretty cool. The 0, though, if you calculate it, is going to be the same, better be the same as 0.73. That's the point of the problem. Are we cool? All right, and that's a good calculator skill to have. We need to have this down. All right, moving on to 37. Questions on 37. What about B? I think that had B. Find the 0, that's what I did. Yeah. So they're the same. The intersection is 0.739. The 0 of that is 0.739. It's the same.
How would you go minus this?
It is the same. Whether you, it doesn't matter. If I want to start here and say where they're equal, do you agree? If I want to make it a 0, I could either move this over here and call it negative x plus cosine of x and find where that's 0, or I could move cosine over there. So it doesn't matter. Although I wrote it differently, it's the same. Okay. Although the graph would be cooler, it would be this now instead, but it would still have the same. All right, set 37. Questions on 37. 14. Did somebody say 7? I didn't hear.
78.
78.
Yeah,
78.
in the first box.
Oh, I got you. Now I remember.
7.
7.
No, 13.
Not 7.
Well, 7 and 13.
7 and 13. All right, there we go. Let me paste that 78. I'm going to get this document up here and loaded. 7 recent. 7. Where's 37? There it is. Okay, 14. Is 14 replaced? It is. Okay, so here we go. All right, this kind of goes to, I'm debating, because you guys are doing pretty well, I'm debating whether to start you with AP for your responses tomorrow and give you a free response and see how it goes. Come on, don't you want to say, yeah, let's give it a go.
Extra credit.
Extra credit. You're going to have to learn these AP problems eventually, I think. You're taking the AP test someday. So, how did the derivative go? Is it A and B or just B? Both. All right. Let's verify you did the derivative correctly. Now, this I feel like you should be able to do. There are some danger places, though. The product tool in there and the negative in there, huge sources of error. So, good thing we did an example with those issues in your notes. Of course, if you use your notes. When I take the derivative of each, I take the derivative on the function, then the derivative on the variable with respect to x. So the derivative of this is 2 halves x to the first, then derivative of x with respect to x, which is just 1, right? Derivative of this is, derivative of the outside is 2y. Then the derivative of the variable with respect to x is dy dx. All right, now here's where I say, oh boy, I've made this mistake a lot. Slow it down and go careful. I'm going to think of this like this, so I don't mess up the negative. Okay, I'm going to attach that negative to the x, and I'm going to use the product rule. First stays the same, negative x, plus derivative of the second is dy dx, plus second stays the same, y, times the derivative of the first, that's the derivative of negative x, negative 1. Derivative of negative 3 is 0, and the derivative of 0 is 0. Okay. Check to see that you have negatives on both of those terms in the product rule. You should have both are negative. Okie dokie. Now if I collect my dy dx's, these two terms have a dy dx. If I keep them on this side of the equation, then I would have 2y minus x, and the dy dx, if I factored it out, would be outside. Everything else then, I'll call it the square terms, must be brought over to the other side. When I bring them over to the other side, what do they become? Y minus x, or negative x plus y, if you like, whichever you prefer. Do you follow? And therefore, dy dx is y minus x divided by 2y minus x. Cool? Okay then. Find all points on the curve where there's a horizontal tangent. Look at dy dx equals 0 and on the original equation. That might be the part that pooped you out. If it's a horizontal tangent, then the derivative is 0. Now that means that the top is 0. If the bottom is 0, that's a vertical tangent and it's undefined, not a horizontal tangent that's 0. So in terms of solutions to this, I don't want to look at both of these equaling 0. I just want to say what makes y minus x equals 0. And that's that y equals x. Now here's the confusing part. Okay, so there's a horizontal tangent where y equals x. This is where visuals kind of fail. Any point where y equals x would be here, right? You agree? Unfortunately, that's not what the original curve looks like. The original curve is some crazy ellipse that's rotating. All right? We haven't talked about that, so you'll have to take my word for it. But the ellipse might look like this. I'm not finding any old places where y equals x. I'm finding places on the curve where y equals x. So it's not just this condition. This condition takes care of the slope equaling 0, but I need to also add on, not only does y equal x, but it's on the curve. So these points, I need to use this with on the curve. Well then, substitute to put those two conditions together. If I can say that y needs to equal x, then in this case, every x can be replaced by y or vice versa. Do you want to replace the x's and go all y's, or replace the y's and go all x's? Replace the, whatever, I don't care. I'm not even, doesn't matter, it's going to be the same kind of thing anyway. If I replace the x's with y's, I get 1/2 y squared plus y squared minus y squared minus 3 equals 0. Yay? That means 1/2 y squared equals 3. If I knock out the y's and move over the 3, y squared equals 6. So y is plus or minus square root of 6. It says the coordinates points on the curve. So when y is positive root 6, what's that? Positive root 6. And when x is, y is root 6, negative, y is x. All right. That's a good start. We'll talk about it tomorrow, or Monday. 37 is not due, 36 is. Make sure I get 36 today. I will be happy to help you prepare for the test if you come in 7th period or before school. Just let me know. Test is tomorrow. Have a great day.
When is this all done, Dr. Lofton?
I think for you, I have not yet graded it. Or have I graded it? Have I graded it? It's fine. Good thing you're such a good kid. All right. So I need to stop this. Do-do-do.